In our previous video, we talked about searching an array using two different algorithms. The binary search could only work if we knew something about the nature of the data in the array. Binary search worked if the data in the array was sorted. Sorted in this manner means the data you keep in a collection has some natural order or arrangement. You can sort strings alphabetically, where the letter A is lower than the letter Z. Numbers can also be sorted from lower values to higher ones. Lists have a singular order to the data inside of them, but the data inside of them may not be in order. For example, here is a list, or what we could also call an array. The values go from 0, 1, 2, 3, 4, 5. They are necessarily in order. They have an order to them. But the data inside the array is out of order. You can see that 43 comes before 25, comes before 4. In computer design, there are many algorithms that sort data into lists or arrays. Today, we're going to cover the selection sort algorithm. So, in a selection sort, we keep track of two items. We keep track of the starting index and the minimum index. We can call a selection sort find a min, then swap. And this is fairly one of the easiest algorithms to understand, but it's one of the most inefficient ways. So let's start with 0. The first iteration, now if we recall from our last video, iterations are doing a set of operations and repeating that set of operations. Every time we repeat, that's called an iteration. What we're going to do is we're going to track the order of the array every time we do an operation in this algorithm. And we'll keep track of it up here. In the AP exam, you'll be expected to know how a specific sort works by saying at what point in the iteration an array looks like after a sort. So let's start with this. We start off at the beginning. Now you can choose to do it in either way, but the most common way is you start from the lowest and work your way up to the highest. So our starting index is going to be 0. We're going to keep track of the minimum value as we go throughout the array. Right now we're going to say that the smallest value is 43. Now we're going to compare that with the next index. This index has 25. 25 is necessarily smaller than 43, so our new min index has changed from 0 to 1. We're going to keep track of that again. We compare it with index 2. Now index 2 is value 4. 4 is less than 25, so our new min index becomes 2. We compare it to the next item, which is 19. 4 is less than 19, so we're okay there. We go to the next one. 4 is less than 7, so we go to the next one. 4 is less than 5. So we've gone throughout the array and we found the smallest value is in index 2. Now we're going to execute what we call a swap. In essence, all a swap means is we're starting at index 0 and we're going to swap the min index for that value. And that's what we do. Swap the two values in here. So we know that this is locked down. We know this is at least correct. This has the smallest value. Now we increment. So our first iteration is 4, 25, 43, 19, 7, and 20. It's probably good to keep track of what we had before. Our starting index is 43, 25, 4, 19, 7, and 20. So on iteration 1, we've changed these two values. Now we're going to start at index 1. And index 1 becomes our minimum index. We check 25 with 43, still smaller. 25 with 19. 19 is smaller than 25, so our new min index becomes index 3. 19 is greater than 7, so we change our index again to 4. Index 4, and 7 is less than 20. So we've now identified our second smallest number. We then execute a swap, which will swap these two values. And we lock down this next value. So our next iteration is 4, 7, 43, 19, 25, and 20. We start off with the next smallest index, which is 2. Our start index is 2. Our min index is 2, and we go down the list. 19 is bigger, or 19 is smaller, so our min index becomes 3. 19 is smaller than 25 and 20. So we have our smallest indexes here. We execute our swap with the start index, and we lock this down, making this 4, 7, 19, 43, 25, and 20. Start again with 3, 43, and 25. 25 is smaller, 20 is smallest. So I didn't say it goes from 4, min index becomes 4, then min index becomes 5. We execute the swap, lock it down, and our next one 4, 7, 19, 20, 25, 43. Start with 4. Our last iteration, 25 is smaller than 43. We don't do anything here. Four, 7, 19, 20, 25, and 43. Note, even though we ended up on the right array at iteration 4, we didn't know that in our algorithm until we hit our last iteration. The reason why this is inefficient is because one of the reasons why this is inefficient is because it doesn't know that it's complete until it's executed this array that many times. That concludes the demonstration on selection sort.